Hello, welcome to this clip having a look at what affects the enthalpy of solution, lattice enthalpy or hydration enthalpy. Well, they both do, so we're going to have a look at in what circumstances one affects more than the other. Once we've done that, we'll have a look at an exam question that's turned out to be quite applied when people took it. So let's review the process of dissolving. Starting with an ionic lattice, obviously you've got to break that lattice up. So what we do is we reverse the lattice enthalpy, and that gives us the gaseous ions from which the original ionic lattice was made. Then those gaseous ions have to be hydrated by surrounding them with water molecules. And the difference between those two positions in the energy axis on the left-hand side will give us the enthalpy of solution. So looking at hydration a bit closely, we've got a single water molecule which obviously has partial charges. And what happens is that that makes it attract to the surface of the ions. So in the case of sodium chloride, for example, you'll get an attraction between the delta positive hydrogens and the surface of the chloride ion, which is negatively charged, and also an attraction between the delta negative oxygens and the surface of the sodium ion, which is positively charged. So because an attraction is going on, it's equivalent of making a bond. So therefore energy is released and the enthalpy of hydration is always exothermic. However, how exothermic depends on the size of the ion. So larger ions attract water less strongly, so therefore the enthalpy of hydration becomes less exothermic as you go down the group. You can see in the examples in the table, you've got group 1 and group 17. Now what also happens going down a group is the attraction between the positive and negative ions starts to become less exothermic too, because the size of the ion will influence the level of nuclear attraction it exerts in any incoming oppositely charged cations. So we can represent this in a Born-Haber cycle by three things: lattice enthalpy, solution enthalpy, and hydration enthalpy. So what we do is we take the negative of the lattice enthalpy, the idea of it being dissociated, and we follow an indirect route to try and work out delta H sol by Hess's law. So if we take an example and put the arrows in again, you can insert the numbers. So delta sol H is minus delta LEH plus the total of the hydration enthalpies. So plus 711, which is the opposite of minus 711, seeing which direction the pink arrow is going in, added to minus 685, which is the total of the hydration enthalpies, gives us positive 26. Now what's important to remember is the balance between the lattice enthalpy and the hydration enthalpies determines whether delta sol H is endothermic or exothermic. So if the magnitude of the lattice enthalpy is larger than that of the total of the hydration enthalpies, in other words we say it's more exothermic, then delta sol H will be endothermic. Conversely, if the opposite way around is happening and the magnitude of the lattice enthalpy is smaller than that of the total of the hydration enthalpies, we say that delta sol H is exothermic. So that takes us to our exam question. So they're saying that the enthalpy changes of solution of the magnesium halide show a trend from MgF2 to MgI2, and they want us to explain why it's difficult to predict whether the enthalpy change of solution becomes more or less exothermic as you go down the group. So going back to our little diagram which had chloride, bromide and iodide, as you go down the group the halide ion gets bigger. Now it's important to say the ionic radius, not the atomic radius, because it's not atoms we're talking about, it's ions. So like we said before, the attraction between the magnesium 2+ and the halide ion weakens. It gets less strong down the group, making the lattice enthalpy less exothermic. In addition, the attraction between the water molecules in the solvent and the halide ion also gets less strong down the group, and this in turn makes the hydration enthalpy also less exothermic. So if they're getting less exothermic together, it's quite difficult to work out the balance between them. So in other words, it's hard to predict whether delta sol H will in turn be more or less exothermic down the group. Okay, I hope you found this useful. Thanks for listening. Until next time, see you soon.